Welcome guys, this is my How to Integrate series, part 1. This is for Calculus 2 students and AP Calculus students, and today we're just going to be covering the very basics of integration. This includes indefinite integration and definite integration. We'll be covering antidifferentiation and the fundamental theorem of calculus alongside some properties. I will be refining this series as we go along. I'll be getting better equipment. Right now this is just on my phone with no editing, just whatever take is good. And yeah, one take. So be expecting this to be kind of bad, but I'm just trying to learn how to teach, essentially. So I've already pre-written out all that we're going to need to know, and I'll just be working through some examples later on. So first thing we need to know is the difference between indefinite integration and definite integration. These are two different things that are pretty related, but have also a lot of differences. Indefinite integration is when there's no a to b, it's just the integral symbol, and it's just a symbol for antidifferentiation. What is antidifferentiation? Well, that's a big word, but basically it means you're finding the function whose derivative is that. You're finding the family of functions, and we'll get a little bit more into detail of that. Finding the family of functions whose derivative is f. Definite integration is finding the area under the curve f on the interval a to b. And there's also other ways of interpreting that. So for antidifferentiation, we first need to know our derivatives. So from Calc 1, we've learned all these derivatives alongside a few more. But for the sake of room, I've just got all the important ones. So, and also, we're going to be using some derivative rules, such as the derivative of a sum of functions is the sum of the individual derivatives. We also, of course, need to know the product rule, left d right plus right d left, and the chain rule, which is very important for next video when we talk about u substitution. But for now, we're just talking about antidifferentiation, and it won't be as important, but we will have an example that uses that. So, when antidifferentiating, you are finding the family of functions whose derivative is f. So, think about this. The derivative of all these functions is the exact same. These are all constants. So that means that the derivative of function is the same, even though all the original functions differ by a constant. So that's why whenever you're doing antidifferentiation, we account for this by adding a constant c. So an example of this would be the integral or antiderivative of oh man, this is kind of shaky. E to the x, I'll be getting a tripod, don't worry. E to the x dx equals e to the x plus c. And why is that? Well, it's because this is the family of functions that satisfy that its derivative is this, exactly this. Because the derivative of a constant is 0. We should already know that. So now let's just do some antiderivatives. So the first one, we're going to learn the reverse power rule, as a lot of people like to call it. So problem 1, integral of x to the n dx. So first off, we know that the derivative of x to the n is, we know this as the power rule, n times n minus 1, x to the n minus 1. So when we integrate this, we know that the integral, we should know that the integral of n, we're going to integrate both sides here. We can do that, but just as long as we add the constant. We know that the integral of x to the n, of n times x to the n minus 1 dx should equal x to the n. So what would we have to do to this in order to get here? One thing we could do is add 1 to the exponent and then divide by the new power. The 1's will cancel. This will just become n times x to the 1's will also cancel up here, n over n. The n's can now cancel, and we're just left with x to the n. So in putting this in better terms, we add 1 to the exponent, then divide by the new exponent. So a better way of putting this would be x to the n plus 1 all over n plus 1. We add 1 to the exponent, then divide by the new exponent, plus c. We have to put that for n does not equal 0, or 1, negative 1. And we'll sort of see that later in this video. But we can see that already right now, that if n was negative 1, we'd have an undefined term. So that's the first one. Second one is the integral of e to the x, or the antiderivative of e to the x dx. We know the derivative of e to the x is e to the x. So that means the antiderivative of e to the x should be e to the x plus c. We can always check our answers by differentiating them. When we're working with antidifferentiation, you can always just take the derivative of your answer and you can check it. And this has helped me out on my exams too. So we know, so if we take the derivative of this, the derivative of e to the x is e to the x, and then the derivative of c is just 0. So it's just e to the x. That is our answer. 3. Integral of cosine t dt. So an important thing I forgot to mention, but I should mention now, is that this variable is called the variable of integration. This dt right here, it means what variable we're integrating. So that means that the cosine is the function, or is the function of t. We're only finding the antiderivative of the functions of t. And this gets very important when you do multivariable calculus with double integrals and stuff like that, where you're changing variables. But right now, since we only have one variable, it's kind of the same as if we had an x there. We just find the antiderivative. So right now, we know that the derivative of sine x is cosine x. So that means the antiderivative of cosine x is sine x plus c. Next one, 4. Integral of 1 over x dx. So this one is a little interesting. You should know from Calc 1, though, that the derivative of lnx, or the natural log of x, is 1 over x. Some people just say log. They're kind of all the same. So this is going to be lnx plus c, but we're going to have to include the absolute value because that's the proper way of doing it. Ln is not defined for negative numbers, so we have to include the absolute value here. And we'll go into a little bit more explanation in my proving derivatives video of all this stuff, but right now this is just a tutorial on how to integrate. Problem number 5. Integral, oh, that was number 5. Oh, number 4, fine, we'll do that one. Integral of yx plus L times y over, 5 times x dx. So, or well, you can just put an x squared here. So this is going to be, we're going to have to use the constant rule for integrals, where we can, if this is a constant, which in this case it is, it's not it is a variable, but it's not the variable of integration, so we can treat it like a constant. We can actually, well, first off, we can split this into 2 individual antiderivatives. This will be the integral of yx dx plus the integral of ly over 5 x squared dx. that is a rule we can use, and we can sort of derive that from common sense using this rule over here. So now what we do is we can move the constant out, then we can find our antiderivative. So move our constants out, we'll have y times the integral of x, I'm going to put to the 1 dx, plus the integral, ly over 5 times the integral of x squared dx. So we know from the power rule earlier that we add 1 to the exponent and then divide by the new exponent. So what we're going to do, we add 1 to the exponent, 1 plus 1 is 2, and then we divide by the new exponent. So y times x squared over 2 plus ly over 5. We add 1 to the exponent, x. 2 plus 1 is 3. Divide by 3. And this is multiply. So we're not done yet. We can sort of simplify this. We don't have to add our plus c till our final answer. So I'm going to put these in descending powers. This will be x cubed over 5 times 3 is 15. And then ly, I'll put the constants there for some reason, plus y times x squared over 2. There's really no reason you have to put it that way, just that's the way I put it. As long as it's like that, then you should be good. So plus c, don't forget your plus c. It will be counted wrong because it is actually wrong. When you're doing antidifferentiation, you're finding all the functions. Unless it says find an antiderivative, which is very rare, but sometimes it can. So another thing that we're going to have to make use of in this next problem, integral of the base a log of bx. Oh wait, no, we can't do that. Sorry. We'll do sine bx. Sine of bx. Okay. What we can do is what's called the reverse chain rule, or what a lot of people like to call it. Or basically, if you have the antiderivative of f of ax times dx, you multiply by 1 over a times the antiderivative of f of ax plus c, and this is to counteract the chain rule. So if you took the derivative of this, you'd have to multiply by the derivative at the inside, which would be a. So to counteract that, since we only want this, we divide by a, if that makes sense. So we divide by a to counteract the thing that would happen from the chain rule with this a here. So for here, we'll first put our 1 over b. I'm going to leave a little bit of space. And so for sine x, we can put a negative here and a negative here. Why is that? Well, because the negative, we're putting a negative 1, essentially. We're multiplying by negative 1 twice, which would just be 1, which doesn't change the integral at all. So what this negative allows us to do is look for the antiderivative of negative sine x, which is cosine x. So don't forget the cosine bx, but don't forget we also have this negative here. So that means we should put it here also, since we're finding antiderivative of negative sine bx. This will become negative 1 over b times the cosine of bx plus c. Alright. This video is getting a little long, so I'll go ahead and cut off once we finish these examples. 7. Integral of 1 over 2 plus x squared dx. So this looks a little bit familiar with the derivative of tangent x over a, which should be that. Now, a good rule of thumb that people like to remember is instead of trying to remember this whole x over a business, we try to remember that, because arctan comes up a lot in calculus whenever you're using integral calculus, of dx over a squared plus x squared equals 1 over a, to counteract this a, times the inverse tan or arctan of x over a. So that is the general rule of thumb that they like to use in integration because it's easier to remember. So for this case, we'll first rewrite it as in this form. This can equal the integral of dx over, this represented as a square would be the same, so 2 is the same as the square root of 2 squared. I'll put that in parentheses to emphasize it. The square root of 2 squared is just 2. That's an algebraic definition you should know. Plus x squared. So this is now in the form of this. So we can antidifferentiate it using what we already know to get 1 over the square root of 2 times the inverse tan of x over the square root of 2 plus c. That's our answer. The next one is going to require some knowledge of trig derivatives, but it should be simple work. Secant x tangent x plus secant squared 4x dx. So technically you should put parentheses, but no one really cares about whether or not you put parentheses around it or not. Once you put the dx, it's basically assumed that it's the entire thing in between here and the integral sign. So, secant x tan x. Well, to integrate this, we know that the derivative of secant x is secant x tan x. So therefore, the antiderivative of secant x tan x is secant x. So that's the first part. If we skip the step of splitting into two integrals, we know that the first part of the answer should be secant x. Now what about this one? First off, I'm going to put the 1 over 4 because we're going to have to use the reverse chain rule. 1 over 4. So for secant squared, we know that the derivative of tangent x is secant squared x. So that means the antiderivative of secant squared x is tan x. So we should have tan 4x plus c. And there we go. That is our answer. So I only have time for a few more. We'll do these last few examples. Go ahead and start doing these on your own so that you can get the hang of it. Do these examples again on your own and you'll start to understand it. So integral of 5 e to the theta plus 3 sine of 2 theta, and I'm also very sorry for the shaky camera quality. I'll be getting an actual camera soon. This is just on my phone in one take without editing. And that's why it's kind of bad, but I'll be upgrading soon. Don't worry, within about a couple months. We'll skip this step of splitting it into two integrals. We can do 5 times the antiderivative of e to the theta. Well, since our constant integration is theta, we can treat it as the same as antiderivative e to the x, which is just e to the x, or theta in this case. Now, first, we'll do the reverse chain rule and the constant rule. This will become 3 halves, so we multiply by 1/2 to undo the chain rule. And we also have the constant 3. And I shouldn't have put a plus there. I should have just put a space. Because what we know from earlier is that the antiderivative of sine x, what we can do is multiply by negative and negative to not confuse the signs. But basically, the antiderivative of sine x is negative cosine x. That's just something you should get the feeling of. So this will be minus cosine of 2 theta plus c. So if you're worried about like not getting this, just know that it just requires you to know all of this, which if you don't know from your calculus class, which you shouldn't have been able to pass if you didn't know all these. I mean, I guess you could have forgotten these ones, that's fine. But, you know, calculus and just math in general requires you to know this stuff from before. You can't just forget about it. That happens a lot on tests and all sorts of subjects where you just study for a test and boom, you're done with it forever. Well, in math and a lot of other, degrees, especially in science, you're not done with it forever. You will see it come up again and you'll be panicking because, oh man, I forgot everything and I have to relearn it. So don't make that mistake. So this is our first composite function and product, whatever. We can use this utilizing the chain rule. We'll learn something called U substitution in 2 videos from now, because I'm gonna skip the fundamental theorem for next video. But the moral of the story is, think about the chain rule. Chain rule says the derivative of f of g of x is f of g of x times the derivative of the inside, which is g prime of x. So what do we see here? We see f is e to the something. That something is sin x. Now we know that the derivative of sin x is cosine x. So what we see here is f of g of x times g prime of x. So that means that we know that its antiderivative is just f of g of x plus c. And our f is e to the something. That something is sin x plus c. And yes, this will become very important once we learn U substitution. So number 11 this is a very interesting one. E to the x times 1 over x plus ln x dx. So right now, if we split it into 2 sums by first FOILing it out, we would get something non-elementary. But the sum of these 2 integrals will result in something kind of familiar from Calc 1. If we have e to the x, let's just distribute. We have e to the x over x plus e to the x ln x. Now, what does this look like? Well, we remember the product rule. Where is it? Yeah, right here. Derivative of fg of x is f of x g prime of x plus g of x f prime of x. Left d right plus right d left, or 1d2 plus 2d1. Those are ways to remember it. What do we see here? Well, let's just assume that this is our thing. We have left e to the x, or no, yeah, right here. Left d right. What is our left? E to the x. D right is our 1 over x, plus right, our ln x, d left. So we can sort of make a guess here that our function would be e to the x ln x. We could put the absolute value if we want. And we can check this by differentiating our answer. So we can just see here that this is in the form of right d left plus left d right. And that is how we arrived at our answer. It's because it's the product rule. So that's the same thing. So we see that the derivative of e to the x ln x is this. So therefore, it's the antiderivative of this is e to the x times ln x. So our last one is a bit of a very long-winded, complicated one. We have the integral of cotangent squared x times sine x e to the sine x minus secant squared x e to the sine x dx. If you saw my 250 integrals video, then you would know that this is number 99. So I might run out of space here, but we're going to rewrite this as something. We're going to rewrite this as sine x e to the sine x. I'm going to leave a space. This will be sine x times e to the x. We have a space here. I might need a bit more. Whatever. We'll just leave it like this. And then, well, I'll leave the space here. Minus secant squared x e to the sine x all over the reciprocal of cotangent squared is tangent squared. Now, what does this remind you of? If you somehow remembered it, it's the quotient rule, which I didn't write down now. But basically, we have the derivative of f over g. I'll just put u over v because it's easier to write down in space. D of u over v is, I like to remember, low v, d high du, minus high u, d low dv, all over the square of what's below, v squared. Or you can use h and l for high and low. Low d high minus high d low over the square of what's below. So we see that tangent is squared. So we can assume that that's our high. Or no, that's our low. What's our high though? We want to show that this is in the form of low d high minus high d low. So how can we write this as low d high minus high d low? I'm going to multiply by cosine x, this term right here, by cosine x over cosine x. And the reason for that is that this becomes tan x. So we have the low and the d high. Well, our high, we can guess sort of that it's e to the sine x because this is our d low right here, secant squared x. So that means e to the sine x cosine x, which we saw from earlier. Where is it? Right here. The derivative of e to the sine x is e to the sine x cosine x. So we see that this is our d high. So we have tan x, sine x over cos x, d high, so which is our low, d high minus high, this is our high right here, high d low over the square of what's below. So that means it has to equal our e to the sine x, which is our high, over tan x plus c. And that is the answer. So this was the introduction to basic integration. Next video we'll be looking at definite integration and some properties of integrals. And if it doesn't go long, we'll be looking at some trig integrals. So these are our rules and these are our integrals. If you already feel comfortable with our topics, go ahead and try these. Anyways, make sure you hit the like button and subscribe to see more content as soon as this arrives. I'll be trying to get better quality stuff like a better camera, actual microphone, actual editing software, all that good stuff. Within about a month or two, I'll be able to afford all the gear necessary to actually make this into something sort of professional looking. But anyways, thank you guys and goodbye.